Hello Year 13, hi. This is the late night session of Simple Harmonic Motion. But in all reality, this is lesson 1 of Simple Harmonic Motion. It is the basic idea of what it is and the 2 conditions of it. So Simple Harmonic Motion is an oscillation, or you can call it a wiggle if you want, but that's not in the exam. So it's an oscillation which has a fixed time constant, and the net force is directed to the equilibrium position and is directly proportional to displacement. Let me explain what all that means. This thing here is a fishing weight between 2 springs. All right. When it is stationary, so as in not moving, it is at its equilibrium position. Why? Well, because the force pulling it that way is equal and opposite to the force pulling it that way, which means that the left and the right forces cancel out. It's got no net force horizontally. Also, the weight force is cancelled by the support force. Now that's easy to understand, isn't it? Because we did it last year. As regards to the time period, if I pull this over and let go, it wiggles, it oscillates backwards and forwards. That time period is fixed, so regardless whether I pull it a long way back and let go of it, very good one, or if I pull it a short way back and let go of it, the time period, the time it takes to get from here to here and back to here, is fixed. Or the time it takes to get from here, travelling that way, so it goes and then it will come all the way back, and then it will go that way. So that time period for it to do one oscillation is a fixed quantity. That's condition 1, and I wrote it here for you. Okay, now the other one, the other condition, if you look at the way this works, if you remember from Hooke's law last year, we said that the more the extension of a spring, the bigger the force. That's Hooke's law, which is F equals Kx, where K is the spring constant and X is the extension. I can put it here if you want. So F equals Kx, but that's for springs. Now the spring is not the only way of doing simple harmonic motion, so don't take this as the definitive. It just works for springs, particularly horizontal ones like this. So if I pull this back, then the more I pull it back, the bigger the force, which means that the larger the net force. Now, if you think about it, if I pull it back this way, this spring here is going to exert a force on it that way, which will accelerate it to the equilibrium position. When it gets to the equilibrium position, you know that the forces cancel. So when displacement is 0, the net force is also 0. That's an important point to recognise. Why this second law is in here. So the net force is directed to the equilibrium, which means it's directed to the middle. If I pull it this way, then the force is directed that way towards the equilibrium, and is proportional to displacement. So the further from the equilibrium, there you are, long way from the equilibrium, the bigger the force. I'm actually having to pull it quite a lot now, and that's what the second law is. What does that mean? Well, what we'll look at next lesson is what velocity and acceleration do in relation to displacement. So it means that the acceleration is also directed to the equilibrium, because Newton's second law said so. Newton's second law, remember, is F equals ma. Now that is the net force, isn't it? So the net force causing an acceleration has to be directed towards the middle. So if it's over here, then the net force is that way, which means it's going to accelerate that way. The more it is over here, the bigger the acceleration. What that also means, which we'll look at in more detail next lesson, is when it is pulled at its maximum over here, which is called the apex, it's at its maximum acceleration. We'll talk more about that next lesson. That's enough for lesson 1 of Simple Harmonic Motion.